Okay, please start.
Okay, so we continue. Okay, let me just explain. Let me give you, I want to pursue a little digression, which is not immediately related to what we're discussing, but maybe it will give an idea, a good image just to follow. Very, very explicitly. So let's consider, so this is digression. The discrete sign process. The discrete sign. Okay. So we consider a measure on the space of binary sequences. On the space of binary sequences, and just the probability that there are ones and such positions. So omega, let's say K1 equals to omega K2 equals to omega K n equals n. This is the determinant of S chi ai aj and S is more or less the same thing as before, but except in this case that there is a parameter alpha. S alpha kn is sine alpha k minus l over pi k minus l. So this is it's just a discrete cousin of our sign process. It's just a measure on a set of binary sequences. It's not obvious that such measure exists. It's not obvious. It requires separate proof, but allow me to skip it. Just my point is that this is an ergodic measure. It is ergodic. It is mixing of orders and so on and so on. It is also a measure with Kolmogorov property, positive entropy. By the way, it's open problem. What is entropy in this function? Open problem. There are estimates above below, but what is entropy? Open problem. Rather simple estimates can be given using negative correlations. Using negative correlations, it's possible to estimate entropy in fairly simple ways, but it's open problem. So just by Bernoulli measure, because measure of cylinder is less than appropriate Bernoulli measure, but open problem. Satisfies central limit theorem, but variance of the number of particles grows logarithmically. Variance of number of particles grows logarithmically. Number of particles in interval from 0 to n is logarithmic, as opposed to square root of n that it would have been for Bernoulli measure. So this is the difference. This is just a cousin. For this cousin also, it is useful to formulate a very beautiful property, the so-called Gauche-Perez rigidity. Which is just the property that if I know, so imagine I know the whole sequence. Imagine I know the whole sequence, the particles and the holes. So here I have, in some positions I have particles, and in some other positions I have holes, particles and holes. But here at position 0, I don't know. So in fact, it is possible almost surely to determine what happens at position 0 from what happens. It is possible to determine almost surely. This is quite unusual property. In fact, it follows from the spectral measure. Spectral measure of the function omega 0 is like this. This is the spectral measure. And from this property of spectral measure, it is possible to derive this property. Since it's a digression, please allow me to be very brief. There is a paper joint work with Dabrowski and Shu in electronic theory. In electronic theory systems. And just in this paper of ours, it is possible, there is detailed investigation of this property and of spectral analysis of this Gauss-Perez rigidity. Gauss-Perez rigidity. In the broadest terms, just please allow me to finish one sentence. In the broadest terms, this goes back to the paper of Kolmogorov in 1941. Yes, excuse me, yes.
So when we talk about the spectral measure, you mean what?
Just measure correlations, just measure that this function omega 0 generates an O2. Just the usual spectral measure for electronic theory, just the measure that the autocorrelations of the function. So, and it's possible to compute it explicitly. I referred to this paper, it's possible to compute it explicitly. Okay, so this just to give you an idea. So precisely, if now I take a bigger interval, if I take a bigger interval, and I know the configuration outside, then I don't know the configuration inside, but I know the number of particles inside. Given the outside, I know the number of particles inside. This is what it means. Given the configuration outside, I know the number of particles inside. Particles inside. Now, the fact that I know the number, but I don't know the positions, this is my result, that the positions cannot be determined because there are these quasi-symmetries. So the action of the infinite symmetric group, it does not preserve the measure. So this measure, which I mean this, is quasi-invariant, under the action of infinite symmetric. Under the action of the infinite symmetric. Is quasi-invariant under the action of the infinite symmetric. Infinite symmetric group is a group of finite permutations. So it is quasi-invariant under the action of infinite symmetric group. So just what do I want to say? I want to say that
so S infinity is the group of all permutations.
Finite. All finite permutations.
Okay.
It's countable group.
Okay.
It's countable group. So yes, exactly. And I want to say that there is a difference between this situation and the situation of continuous, which we discussed yesterday. Just here, of course, infinite permutations, they change in every class. Because, you know, infinite permutation, you cannot permute little bits. So move things a little bit, but here it's not possible. You have to permute, and so they change in every class. It's quasi-invariant under S infinity, but not under anything else. This is proved by Bolshinsky. Okay, so now,
Can I take the opportunity to make a question?
Yes, of course.
Regarding with yesterday, so the sine process measure.
Yes.
Yes. Is it also quasi-invariant under some?
Yes, but that's what we discussed yesterday.
Yeah.
Under compactly supported and also sufficiently fast decaying at infinity, so that the multiplicative functional is well defined in integral. That is what we discussed. That is exactly what we discussed yesterday. So in that case, it is possible to have non-compactly supported, sufficiently fast decaying at infinity different voltages.
Okay. Okay,
But
so
not in
it's
this.
the group is a group of non-compactly supported, but with
Sufficiently with the fast, yes, with the fast rate of decay tendency.
diffeomorphisms of the real one.
That's exactly right. Diffeomorphisms of the real. That's quite precise. Diffeomorphisms of the real.
Yes, by decay you mean that converge to the identity, so near infinity the diffeomorphism.
Right. Of course. Well,
Yes.
yes. So it converges to the identity, but we need more. It certainly we require it to converge to the identity, but in fact we need more. We need convergence of some Sobolev norms. We need more, in fact. In fact, we need more. Okay, so this much for the digression. Okay, so now, if it's okay, I want to go back to the main subject. So this just was a digression. I want to go back to the main subject. So the main subject is the behavior of additive functionals under my sign process. So let us be precise. So I have my sign process. So just now, continuous sign process. We go back to continuous sign process. So I have my sign kernel in continuous sign. I have the holomorphic function that we discussed already many times. So I consider logarithm, and in fact, I consider a regularized logarithm. So there will be, excuse me, the notation will be a little bit heavy, but not very. So I do a little bit of transformation. So I move my t. I move my t away from the real line, but also I move my x away from the real line. So this is the quantity that I consider. Let us be a little bit. So excuse me, maybe I put S here, it will be clear. Because this T, it is sort of the same, but not S here, it will be clear. Okay, so what I want to say? I want to say I am interested in the following question, in the following statement, that Jxt with one particle removed, so this is the product 1 minus t over x in x with one particle removed. I want to prove that this quantity is not in L2. This is what I want to prove. That this quantity is not in L2. So it will be more convenient for me to shift everything by IA. Just to shift everything away from. So here, if I take the logarithm of this quantity, so I would get logarithm x minus t minus logarithm x. So this t corresponds to this d, in fact. excuse me, I miswrote. So in fact, I miswrote. I shift just x. That's right. So instead of this, I take logarithm x minus t squared plus a squared minus logarithm x squared plus a squared. So instead of considering this ratio over x, I put plus IA both to numerator and to denominator. Well, obviously, just by shifting just by x. Right. Just by shifting x. So this is just more convenient for me, just to shift x. In fact, this shift of x does not have an impact on this square integrability. This shift of x does not have an impact on square integrability. Why? Why? So let me explain why. It's very simple remark, but let me just be very precise. Simple remark. So Jx be in L2 or not in L2 at this point, if and only if Jx plus Ia P is or is not in L2. So, and why is this? Why is this? Let me explain. So, in fact, shifting the zeros does not change the fact that a function is or is not a function in any Wiener space. So let us be a little bit more precise. So I write product 1 minus t x plus I, which is the same as product x plus IA minus t over x plus. So in fact, so I put it that I can put the absolute values. Let's put that here. So I have this product. So now I have product this x squared plus a squared, this one. But this I can replace by x squared. This is just a constant which only depends on x, it does not depend on t. And then I have the product t minus x plus a over x, which is just jx of t plus a. Excuse me, I have to multiply by this. So I have the following identity, the following very simple identity, that g x plus a t is equal to gx and so I put absolute square times product x square x. But we remember, but such product converges. We remember that x, it's roughly like n. So such product converges. So this is just a constant, and these two and this one. So Bailey-Wiener space is invariant under shifts of t. Bailey-Wiener space is invariant under shifts of t. If a function belongs to Bailey-Wiener space, then if we shift it, it belongs to Bailey-Wiener space. Let's recall what does mean Bailey-Wiener space. Bailey-Wiener space means that it's a function whose Fourier transform is compactly supported. But if we shift in such direction, we multiply it by exponential, but it's compactly supported, it doesn't change. And of course, being in L2, also that generally speaking, obviously, shifting like this can change whether a function is or is not in L2 because we multiply by some exponential. But since it's compactly supported, it doesn't change. Okay. So, end of story. I can consider this. This is more convenient for me to consider. Why? Because this function is more regular. Logarithm has singularity at 0, and this one doesn't. This is just a convention of convenience. Okay, perfect. So now we continue with the study of this function. And now, please allow me to, again, just not to be very heavy-handed, but this is one of the main points of the paper, but just not to be excessively heavy-handed. Let me just make it a little bit, let me be a little bit, how should I say, allow me a little bit of hand-waving. We can absolutely make all the computations in a very precise way, but for the moment, allow me a little bit of hand-waving. So we discussed that the variance of a negative functional, so SF being some function over one, the variance of a negative functional is equal to this quantity. Where this is the sine curve. So in fact, the main, it's already clear from the form, the main term in this is the Sobolev norm. The main term in this is the Sobolev norm. Now, the main term in this is the Sobolev norm. Now, what I want to say, here comes the hand-waving part, is that in fact, the expectation of the exponential set is also in fact, so this is 1/2 Sobolev norm. You know, 1/2 Sobolev norm is one of the most useful norms in history of analysis. Just 1/2 Sobolev. It's semi-norm, so it's just occurs everywhere. Just it has this property, it occurs everywhere. This 1/2 Sobolev norm, which is just integral absolute value of lambda f epsilon squared. It occurs everywhere. Okay, so I want to say that this is equal to exponential of 1/2 lambda squared. And then there is error term, and this is precisely where I ask for your indulgence. So this is precisely what at this moment I want to hide under the carpet. Then there is error term. The important part is that error term is less than 1 when lambda is real, and in some sense, if lambda is sufficiently small, it's close to 1. So there is a certain normality. For example, there is central limit theorem of Soshnikov, which says that S, if I take F and divide by some R like this, so I consider my function like this. Yes? Sobolev norm, 1/2 Sobolev norm. Why? Well, one of the reasons, there are many reasons, but one of the reasons why it is so ubiquitous is that it is invariant under dilations. It is invariant under dilations. And just when I do this, so the L1 norm explodes, the H1 norm decays, and the 1/2 norm doesn't change. Right? Okay. So then this quantity doesn't change. And in fact, if we divide by the solid norm, then this converges to the normal distribution. Please observe that this is convergence without normalization. The variance of random variables remains bounded. So cancellation is so fine that there is limit distribution without any division by something going to infinity, right? Everything cancels out. Everything cancels out. So this is very beautiful central limit theorem of Soshnikov. So this error term can be controlled, but for the moment, please allow me to be lighthearted about this. Okay. So, and now we proceed to the study of this quantity, Okay. So our aim is to see. So from the very form, you can see that different from the very form of this expression, you can see that different frequencies are sort of independent. Different frequencies are sort of independent. So it is very meaningful, it makes a lot of sense to localize in frequency space and to see how these frequencies interact. So we need to take Fourier transform. This, fortunately, we can do it very explicitly. Okay, so we need to take Fourier transform. That's already from here. We need to take Fourier transform of the function phi. This can be done very explicitly. This allows for an explicit computation. Let me write it in this form. So the function phi is shift. So, okay, let me write it and then you will see. Let me just write it and then it will become whatever. So this is the Fourier transform. And already you can see why I wanted this A. because I wanted this exponential decay. Okay, where did I take this Fourier transform from? I took this Fourier transform from the fact that, of course, 1 over S plus IA is equal to the integral e to the minus lambda A plus is lambda, something like this. So it's the Fourier transform from 0 to infinity. So it is the Fourier transform of this function, but restricted from 0 to infinity. Then I take S minus, and it becomes the same function with absolute value. Then there is a shift, and then there is the antiderivative. So end of story. Okay. So now I will want to localize this quantity in terms of, I want to localize this quantity in terms of frequency. So I will want to do the following thing. So I consider, of course, the first of all, I will need this 1 over lambda is a little bit inconvenient for me. I will want to smoothen it a little bit. This is just purely technical thing. So I will just want to smooth it a little bit. And I take LxDS just a little bit of smoothing the shift back. It doesn't change things much, in fact, almost not at all. And so here I can write just it's just one more level of averaging here. So, and of course, I will need also the decomposition in positive and negative Fourier part. I will also need the decomposition of positive and negative Fourier part. Okay, so now comes the main point. Now comes the main point. So I am able to, now I'm able to localize frequencies. So the main frequencies for me will be frequencies that are how to explain myself. Excuse me, let me say it the following way. So the frequencies become, as soon as D, so let me put it this way. As soon as D and D1 and D2, so let's consider D1 and D2. As soon as D1 and D2 become distant enough. So, okay, excuse me. Let me say one very simple thing. So if I integrate e to the I lambda d1 minus d2, then such integral is bounded. It's not possible to debate this, right? So such integral is in fact bounded. So
Sasha, can you say a word on what's the name of this regularization? So because looking at the expressions, I don't see the name.
here it is. Yes, you see it. Here it is. Exponential decay.
No, I mean when you.
I mean this case.
Yes.
Yes. So yes, just a second. Yes, there is gain. There is quite explicit gain. Just how to explain myself. Just a second. It's sort of a smoothing effect. Just excuse me, just a second. I will say this. Let me just say this very clearly. We'll see it in a moment. We'll see it in a moment with computations. It will be.
But you don't need to show computations. You can say words that this function. What
is smoother?
Smoother. So when is C1 or can you get higher smoothness?
Just a second. How to explain this? No, they are. So you see, I will have to subtract this one. So yes, let me, okay, it's a little bit tricky to explain because it comes from the computation. So I will have to subtract this one. This one, it will in fact be in the way of my independence estimates. And then for how do I say, for different D1 and D2, so this one will disappear. And then for different D1 and D2 at very low frequency, when exponential will also disappear, this smoothing will be very convenient. The smoothing will make things very convenient. It's just part of the computation. Okay? Okay. So now let me just say, let me just maybe say in words. Let me just say in words that the smoothing the independence. So I want to localize. I take my frequencies. So I'm only interested in low frequencies because high frequencies are negligible. I take my frequencies from 1 to, I choose some large parameter t to t inverse. And I divide these frequencies in logarithmically uniform pieces. So I write from 1 to t, then I push t, and then I have t 1 minus 4. These are my frequencies, my frequency range. Please observe that the variance, because the variance, again, the variance is the Sobolev norm. The Sobolev norm of this quantity, or this average, it doesn't matter for this, is of the order of logarithm of d. Is on the order of logarithm of d. Is on the order of logarithm of d. Why? You might ask why does d play a role? For a very simple reason, because in fact, when one multiplies, one gets, well, the exponential with itself cancels out. So one gets 1 over lambda. But in fact, one gets this 1 over lambda up to lambda equal to 1 over d. Up to lambda equal to 1 over d. So one integrates 1 over lambda up to lambda equal 1 over d. Please observe that you might say we have square. So lambda times lambda is 1 over lambda squared. But no, because we multiply by lambda, we consider Sobolev norm. So it's 1 over lambda up to lambda equal to 1 over d. This is what we're thinking. So each of these has, so d will be taken on the order of t, and each of these takes equal share of variance. Furthermore, clearly, well, this is just the definition, different frequency ranges are independent, but most important, when D1 and D2 are bigger than the frequency range, then they also become independent because of this. Because of this. When I integrate this over high frequency, I get bounded amount. Okay, so let me just write the statement maybe without going into computations. So I need to subtract this 1 over lambda. So I take this sort of average, which is ft plus, which is just we define ft, average ft, so ft plus. Plus refers to projection on the positive Fourier offline. So ft plus is just 1 over lambda times the inverse 1. So I'm just subtracting the average. So obviously phi ft is just ft, so ft at this point is just obviously 1 over absolute value of lambda the inverse 1 plus minus 1 minus the inverse. So now we subtract the average. So we subtract the average. We restrict to the Fourier, to the, let me write it in different spots. We restrict in Fourier space so I take my f dA, I substitute f t. Okay, I take this Fourier transform. I restrict to the corresponding frequency range. And I take inverse Fourier transform. Yes. Yes. So this is just a restriction to Fourier space. And so now just the statement is that these quantities are essentially independent. These quantities are essentially independent. This is the whole statement. These quantities are essentially independent. So the probability that these quantities, so the main claim is that these quantities, main claim is that the quantities S, F, DAL and S, F, D, so let's say D1 and D2AL are essentially independent, essentially in a certain very specific sense. So in fact, the error is independent up to a very small error, are essentially independent. As soon as, and this is the key point, D1 minus D2 is bigger than T as soon as the difference is bigger than the frequency. L plus 1, L. No, that's it. That's precise. No, excuse me. That's correct. This is
T is a given parameter.
that no, T will go to infinity.
Yeah.
So this essentially will become better as T goes to infinity.
can you just say a bit, so this is a definition F plus DA.
Yes.
This is the definition of
A function. Yes.
of a function.
Yes.
But what is the role played by this function in this plane? Or I used to see, so you are defining different functions. And I want to understand what's the role.
But this is just decomposition, excuse me. This is some, maybe this will become clearer.
This is the
D, of course.
Okay.
This is some, I'm just cutting into pieces.
Okay. In L.
In L.
No, but in the plus, so the...
No, plus is just for convenience. Plus is just for convenience of writing. It's all the same in the minus. Plus is just for convenience of writing to avoid formulas of this type. In the minus, it's the same. No, this is just for convenience of writing.
Okay. So you are using for each function the decomposition in its positive and negative parts?
Fourier, positive, Fourier negative, yes. Fourier positive and Fourier negative, yes. Fourier positive and Fourier negative, yes. Okay. So my next aim is to show that this independence is enough. So I want this independence again. I somehow try to hide computations on the carpet. I'm very happy to do them, but I thought that doing computations on the blackboard maybe it's not the most conveys the most information. But I thought maybe rather to explain, it's a very beautiful little argument to explain how from this independence one gets what we want. So it's beautiful, it might be useful also in other contexts too. It's beautiful version of inverse correct and Penn-11. In fact, it's the Penn-Zygmunt in effect. Okay, does that make sense? Okay. So how to derive the desired? So let me just say again. Let me say again what would be the argument? What would be the argument? Since for these quantities individually we know that they are independent, and we know their variance. We know that they do explode high enough so that there exists. So let us recall, what do I want? I want that this quantity is not square integrable. So in fact, I can show that there exist moments when it explodes so that it becomes of the order of, so I want to divide it by 1 power of t, so I needed to explode more than t. So such moments exist. Such moments exist. I can show it. But the question is, maybe there is just one such moment, and that's the end of story. So with positive probability, this function, with positive probability, it is of order 1. Of order 1 as well. Obviously, if a function is of order 1, it cannot be square integrable. But the point is, of course, maybe it's just once of order 1. Maybe it's once of order 1 authenticates. So I want to show you that it's infinitely many times of order 1. Right? That it is of order 1 infinitely many times. And for this precisely, I need to explore my independence. And this is what we will now do. Okay, so if no objections, I will erase all of this. And just I will do a little simple and simple lemma. So we have some events. We have some events. V1 and so on, Vm. So excuse me, I started in wrong way. Let us recall first, excuse me, reminder, Pelizigno. So let's see. Z positive. Then probability that Z is bigger than 1 is greater or equal than E Z squared over E Z. Indeed, so why is this true? Well, why is this true? It's just a version of Cauchy-Bunyakovsky inequality, but let's see. What is the best way of seeing this? Just a second. I am a little. Excuse me, I'm blanking a little bit. So just audience participation. It's something, it's completely simple, it's one line. So just excuse me. So please help me. It's just one line. It follows one line from Cauchy-Bunyakovsky, but excuse me, I'm a little bit on today on just.
So Koszynkowski is the same as the Koszyk-Schwarz.
That's right. 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 It's really something very, very simple, but just excuse me. So just it's something, excuse me, really and really a little bit. So let's denote this probability by Q. Then the expectation of Z is at most 1 minus Q plus integral over Z on this event. Which in terms is less than, clearly, Q square root of EZ squared. Am I writing this correctly? Well, yes. All right. So what do I get? What do I get at the end of the day? What do I get at the end of the day? Just exclude me. This is, yes. Excuse me, I'm saying something, excuse me, I'm saying something completely stupid. Yes, I'm saying something completely stupid, excuse me. I'm saying something completely stupid, excuse me. I'm saying something completely stupid, excuse me, I got confused. Excuse me. Yes. Yes, there we go. Excuse me, yes, I'm saying something completely stupid, yes. Okay, excuse me, there we go. Excuse me. Yes, because in our situation, expectation will be fixed, but this, of course, yes. Now I think it's better. Yes. So, in fact, expectation of Z Maybe we will meet soon, yes. Just 1 second. Just a second, excuse me. So, so I can write EZ. So I get this 1 minus Q plus square root of E Z squared Q. Yes. End of story. There we go. I think now it's good. So EZQ
Wikipedia and see the Pauli Sigmund equality.
Yes.
You are missing a theta before the expected.
Yes.
Plus or equal than theta.
Yes, very good.
And one in the other side, it's 1 minus theta squared.
Yes, very good, excellent. So now, yes, exactly. Thank you very much. I knew I was doing something wrong. Yes, exactly. Now it will. Thank you very much. Yes, now it will be good. Yes, thank you very much. Yes, exactly. Okay. I knew I was doing something wrong. Let's try again. Okay, thank you very much. Absolutely, yes. Now we need to make some mistakes. Exactly. Perfect. Yes, thank you very much. Yes, okay. Third attempt. So expectation. So this we don't know make. So expectation of Z. Expectation of Z is equal to, is less or equal than, well, clearly, theta times expectation of Z times 1 minus Q. Whereas the expectation on this big set, we cannot estimate it in any other way. So we estimate it as Q square root of EZ squared. Because in fact, expectation is less than probability of failure. Expectation is less than square root. This is just Koszyuba-Nikowski. So I hope that now it is going to be good. So let us see.
One minus Q is less or equal than 1, for example.
Excellent point. Yes, in fact, we can, yes, this is very good. Yes, excellent point. Yes. In fact, we can argue very naively, and then we are done. But in fact, now I'm interested myself, excuse me, it is a little bit of improvisation. So what we get if we argue in more precise way? So then we get Q So this is it. So the inequality is proved. End of story. But we can also get right. We can also get a little bit better estimate. In fact, right. We can also say that in fact it is bigger than right. Right. Remark. In fact, we get we obtain Q is bigger than minus theta. Wait, there is really something, still I'm not getting. Ah, yes, because I have square root of Q here. Yes, I was wondering what it is. I was like, yes, there we go. Here I have not Q, but square root of Q. Yes. Yes, now, yes, of course. Yes, that's right. Not Q, but square root of Q, because in fact, right, because I wrote Koshev-Vinikovsky inequality incorrectly. Yes, now this is good. So, but in fact, I can get more, but yes, I can get more because I can write that in fact we obtain square root of Q times EZ squared minus U theta EZ is greater or equal than EZ in minus theta. So in fact, yes. So here we just neglected but in fact we could, for example, substitute instead of Q the smaller value, right? So we could, for example, write square root of Q square root of EZ squared minus this very thing, theta 1 minus theta squared EZ squared over EZ squared. Right, and well, and this would give a somewhat stronger version. So we could say Q is greater than plus EZ squared over EZ squared over this square root of EZ. Yes, we could even say something like that. But okay, but this will be the Pelly-Sigmund inequality in this form will be quite enough for us, in fact. Okay, so now this is the Pelly-Sigmund inequality. Excuse me for just the mistakes, but now we have also both the formulation and the proof. Okay, I erase this remark, and just we We continue. Okay, so these are our events, and we assume that our events are increasingly independent. So what do I mean? What do I mean by this? I formulated this. So we assume, number one, that probability of each event is some quantity, which I denote by rho of n. So it's between two constants. That's C1 and that's rho n is such some number. And secondly, I assume that the probability of the intersection is sufficiently small. It's less than some C3, this rho of n. And then I have some function phi of the difference of j minus k. Okay. So now I claim, so rho of n, I assume rho assumptions. Assumptions are that rho of n are that rho of n is bigger than 1n. And second assumption is the most important one, is that the sum, this is phi n, the sum of phi n of k from 1 to n, is bigger than some constant, actually is less than some constant of n rho. These are the assumptions. So what does this mean? This just means that the sets are of comparable measure and they become, so this is just conditional probability, they become progressively uncorrelated. So then from that, under these assumptions, we have the probability that we have that many of these events will occur. We have that many of these events will occur. That is to say, probability that the sum Vn is bigger than some gamma, which is a constant, times the expectation, which is this n rho n. Please observe that n rho n is just the expectation of sum of expectations. So remark sum of p over n rho n is between two constants. Well, in fact, those very constants, 1 and c. So this probability is bigger than some theta. Well, I put it delta, where gamma and delta only depend on gamma and delta only depend on the constants. There exists gamma and delta depending only on C1, so here is C0, C0, C1, C2, C3, and such that the following. Such that. Okay, so this is the claim. So let me first say why this claim is enough for us. Because what are the VJs? VJs are, you remember, I cut my function in frequency space. So VJs are events that all of these pieces are big. All of these pieces are big. So then it has a certain probability. And the probability of the intersection, well, this is precisely my independence. This is precisely my independence. So n, one should think about n as exponential. So so remember I had my parameter t. So one should think of n as exponential of t. So, right, yes. No, excuse me, I misspoke. One should think of n as t, but excuse me, no, I didn't say this correctly. So one should think of n is precisely t, but this n should be thought. So excuse me, let me connect. So this is formal statement. This formal statement, which we'll formally prove. But let me connect it to the picture of binary tree, which we discussed yesterday. So the picture of binary tree. So VMs are precisely branches of the tree. And so the depth of the tree is this M, where I did my partitioning in frequency space. So in frequency space, I did my partitioning in M. This is a branch of the tree. And phi n is the correlation so rho of n in our situation, rho of n will be n to some power minus theta. So the probability of each event will be exponentially small, but in fact, there are exponentially many events. So the expectation will also be the expectation will also sum up. And phi n of G-K will just be 1 over G. This one is very simple. Let's put plus 1. Will be just 1 over G-K. Okay, so this will be in our situation, in our specific context. Okay. So now let us prove. But the proof is, this is our specific context, but the argument is completely general. The argument is completely general. Okay. So in fact, to prove this, we just need to prove, keeping in mind the Pelly-Zygmunt inequality, in view of the Pelly-Zygmunt inequality, it suffices to prove in view of the Pelly-Zygmunt inequality, it suffices to prove what? That the expectation of what? Of this. Everything okay?
Yeah, this went off, so we lost the.
Shall we put it back? Yes. I'm almost finished. I just need 5 minutes. Not even.
Let me just. I don't know why this happened. I'm in the account. I don't know.
I think we are very calm.
Recording. Okay.
Okay, yes,
Yeah.
yes, I continue. Yes, okay. So we just need, I'm almost done. So I just need to say that this expectation is less than some constant n times rho of n. This is the only thing I need to prove. Because then I'm just using Pauli sigma inequality. Okay, but this is quite precisely so that this is quite precisely what was assumed. So indeed, okay, I erase the Pauli sigma inequality. Indeed. Okay, so I have the diagonal, so this is just equal to the sum. Which we can. So, and let us now check. So the sum is over j and over k. So the sum will be, so for example, I have diagonal term, n times 1. Anyway, so just the expectation, up to a constant. Then I have the off diagonal term. So I have n minus 1. So I have sum n minus so here I put k, okay, n minus l, phi n times rho of n. So, and just estimating, so here some from alpha. And so just estimating very naively, so this is less than C n rho plus n rho n sum phi of L. I obtained what I wanted. And this is end of story. This is end of story. And this is end of story.
Just want to understand when you
Let me just maybe because I erased it, but let me write it again in correct way. So because there was a little bit of confusion with the dignity. Right. Yes, okay, now it's good. Yes, yes. Now I'm ready to answer all the questions.
okay, but I thought you are using assumption, so yeah.
Yes, yes, of
But
course.
then don't forget n rho n squared.
But that's exactly what I want. But that's exactly what I want. Yes, of course, I get n rho n squared. Yeah, excuse me, I miswrote here. Oh, excuse me. Yes, of course. I get n rho n squared. Excuse me. I miswrote here. Excuse me. Yes, I get n rho n squared. That's exactly what I want because the expectation is n rho n. So excuse me, you're completely right. That's exactly what we want. That's exactly what I want. Just the way of writing it, it's just to stress that in fact I need very little. For this argument, I need very, very, very little. So here in my situation, this will be logarithm and this some power. But in fact, I need very, very little. Okay, so and this is how, this just gives you a little glimpse of the argument.
Yeah, thank you so much.
Without technical detail.
Yeah. It was great. I think we learned lots of things. So, well, many things techniques that we didn't know. But, well, personally, I feel eager to look into them.
Okay,
So
thank you very much.
really a wonderful course. Thank you so much.
Thank you.
Yeah. Some guys have to go. Because
Yes, of course.
Yeah. So maybe I stop recording. Well,
Yes.
this will be available. I'll send you the link later. But